It's my honor and pleasure to introduce my friend and colleague, Davide Scaramuzza. Davide is a professor of robotics and perception at the University of Zurich. He did his PhD at the ETH of Zurich and his postdoc at the University of Pennsylvania. He pioneered autonomous vision-based navigation of drones, which inspired the navigation algorithm of the NASA Mars helicopter and a lot of drones challenges. He has won many awards. Just to name a few of them, he will be awarded in a few months with the IEEE Technical Field Award, and he has achieved the IEEE Robotics and Automation Society Early Career Award. Besides his excellent research, he founded 2 companies. He's a co-founder of Zurich Eye, which became Facebook Meta Zurich, which developed the world-leading virtual reality headset MetaQuest. And in 2020, he co-founded Sand, which built autonomous drone for precision agriculture. So I'm super excited to see Davide's presentation, and I hope you are as well. And Davide, please, the stage is yours.
Thank you, Christian, for the nice introduction, and thanks a lot for inviting me here. It's really an honor to be presenting at the European Robotics Forum. Today, I want to tell you the journey that took us to a competition that we organized 2 years ago, that was published only a few months ago, about using vision-based autonomous navigation to defeat the world champions of drone racing. And let me start, actually, with a small spoiler.
One day, I dream I can achieve that. Damn!
You know that's not human.
Insanity.
I don't even know what I just
so
watched.
happy to see that in person. One day, I dream I can achieve that. Damn!
That was one of the world champions of drone racing, but I will talk about that later. Today's talk, it's actually mostly about perception. And let me start from why perception is important. Let me start with an example that most of us can relate to. What you see in this picture, it's a long exposure photo that was taken of a Roomba vacuum cleaning robot until 2017. The robot used to take 20 minutes to clean a bedroom of 20 square meters. The robot was not very smart. It was moving at random. What happened in 2018? The revolution appeared. The first camera was put on a Roomba together with a small computer. The Roomba was using images to build a map of the environment in order to travel smart trajectories. Thanks to perception, the productivity of the vacuum cleaner improved from 20 minutes to 5 minutes. Is it better than humans? No. It takes me about 1 or 2 minutes to vacuum my 20 square meter room, so there is still a lot to improve. Where else has perception made a difference? For example, in improving the agility of humanoid robots or legged robots in general. Most of us know Atlas from Boston Dynamics doing parkour. And this is the success of perception and control. Thanks to perception, the robot uses multiple cameras to build a map of the surrounding environment and predicts the footsteps ahead. And then it uses a model predictive controller in order to track those trajectories. Where else has perception made a difference? On Mars. Thanks to perception, finally, our human society was able to move a robot completely autonomously for the first time on Mars. Were the previous rovers not autonomous? Not really, because the waypoints were sent from Earth, and the latency was about 20 minutes. But you cannot fly with a latency of 20 minutes from Earth with a flying robot. That's why they had to rely on onboard autonomous navigation. And thanks to perception, Ingenuity was able to perform more than 70 autonomous flights until it was retired because of a technical issue a few weeks ago. Another area where perception is making a difference is, for example, in precision agriculture. And there were a lot of talks yesterday and also this morning. Thanks to perception, robots can fly smarter trajectories, be more productive. For example, here, this is a video from our most recent startup, Swind, that is based in the south of India, where we are using autonomous drones with vision-based navigation to fly faster trajectories, be very productive, and spray pesticides, which are, by the way, very toxic for humans. So from all these examples, we observe that thanks to computer vision, mobile robots are becoming autonomous. But the reality is that when you look around, you don't see many robots. You actually still see humans. So humans are still preferred in most applications. And the question is, why is it that? The reason why we do not yet see so many robots around us is because current robots are far from human performance in agility, versatility, and robustness. In my lab, we don't cover all aspects of robotics, but we focus on one specific platform, which are the drones. We chose the drones not because they fly, but because of the research challenges that they raise, with the hope that by solving these very hard problems, we can transfer these research results to other robotic platforms. Our goal is to fly autonomous drones, ideally better than human pilots, one day. How do human pilots navigate drones? Vision-based. They put a camera on board the drone, the camera transmits images to goggles, and then the brain processes the information and sends it to the fingers that act on the joystick. You know, at the beginning, when we started this research, we thought that in order to beat human pilots, we had to actually make decisions faster than human pilots. And we were wrong. In this paper, we studied, using eye tracking, the perceptual latency and behavioral latency of expert human pilots. And what we found was actually quite surprising. Human pilots are very slow. The reaction time is about a quarter of a second, 250 milliseconds. You know how fast are our decision-making algorithms? 20 milliseconds. So they're already faster than humans, but they're not as good as humans. Why? Because humans are better than machines at making decisions in complex situations. And this is the reason why we still don't have autonomous cars, and it will take many decades until we do. You may wonder, why do we care about making, for example, drones more agile? For the same reason why Boston Dynamics is playing parkour, to increase the productivity, to push the boundaries of research. But we also wanted to see whether this is really true. So why flying agile? To increase the drone productivity. There are two reasons for that. First of all, drones like quadcopter or hexacopters, which are called multi-rotor drones, they have a battery that lasts for only 20, 30 minutes. There is not much you can do in 20, 30 minutes. But if you can fly faster, you fly farther. And this is not just a speculation. We published this. What you can see here is the distance traveled in kilometers for a given battery as a function of the flight speed in meters per second. What you can see is that the faster you fly, the farther you fly. But after you reach the optimal speed, it's no longer convenient to fly faster. Why? Because then you encounter, for example, air drag, and you start drawing more energy from the battery. What this plot shows is that there exists an optimal speed. Now, the question that we should ask ourselves is, where do current drone commercial companies lie on this plot? They're here. DJI, Flyability, Skydio are the world-leading drone companies for inspection. But they are not taking fully advantage of the optimal speed. But what we know is that one day they will want to fly at the optimal speed, but we don't know how long that will take because there are many challenges. And that's what we are investigating in my lab. Where are human pilots? Well, especially drone racing pilots. Well, drone racing pilots are not certainly maximizing the distance. They are rather maximizing their wins or minimizing their lap time. So they are on the opposite side of this curve. But I believe that by gamifying sometimes research and by pushing the boundaries beyond what is necessary, the research results that you obtain and the discoveries you make can be useful in general to push research. And that's the reason why we also started working on drone racing and agile robotics. And this research is actually funded by an ERC. Flying drones more agile can actually benefit a lot of areas, such as rescue. Thanks to fast-flying drones, Zipline, a company that has set a business in Rwanda in 2017, they saved tens of thousands of people by delivering blood samples faster than ambulances. Exploration and inspection. In order to increase the productivity of the drone, you need to fly faster. Forest monitoring. Now there is a new X Prize challenge for the team that is able to extinguish most fires in a forest. We are also collaborating in that. Personal air vehicles. Volocopter and Lilium, they are starting to transport passengers with big drones. And then we need to fly faster in order to be productive. NASA. After the success of Ingenuity, NASA is going to put on Mars the Mars Science helicopter in 2030. This helicopter will need to fly 10 kilometers, but to fly 10 kilometers, it will need to fly faster than Ingenuity in order to maximize the productivity within the limited battery life. So let's have a look at the really works on agile flight. We can plot all the state-of-the-art on two axes. On the horizontal axis, we have agility, and on the vertical axis, we have works that rely on external sensors, so like GPS or motion capture systems. Actually, pioneering work on agile flight was done by the group of Andrew Ng and his PhD student at the time, Peter Abil, who demonstrated a flip of a small-scale helicopter using reinforcement learning, but they used a GPS and cameras on the ground. After that, Professor Raffaello D'Andrea and Vijay Kumar at ETH Zurich and University of Pennsylvania in Philadelphia, they started research on using motion capture system to build the control algorithms to demonstrate that actually it is possible to drive quadcopters very agilely. And this is a very historical video. This is a video from Mark Mueller, a former PhD student of D'Andrea, and the drones were playing ping pong or tennis. But they were aided by a motion capture system. What happened in the last 7 years? Research has started to be devoted to using only onboard sensors, especially cameras, because you cannot put a LiDAR on a drone, it's too heavy. But as you can see, while they were relying for the first time on onboard sensors, their agility was limited compared to the reliance on motion capture sensors or GPS. Human pilots? Well, human pilots do not rely on any external infrastructure. But we want to be better than human pilots, okay? Now, let's go into the specifics of vision-based navigation. What is vision-based navigation? Vision-based navigation relies on an onboard camera and a computer to let a drone, first of all, hover and then fly. By the way, drones, flying robots, are one of the few robots that, without seeing, they cannot even stand still. Think about it. A legged robot can remain still with its feet on the ground. So does a car. But a drone that doesn't see a single image will eventually drift and crash. So will, for example, an underwater robot that doesn't see anything. So it's very important not only to be able to see, but also to be able to see texture. And that's the reason why Ingenuity failed after 70 flights, because they flew on a dune without any texture. And the drone just fell and destroyed one of its propellers. How does it work? You use the computer to extract some interest points, features, then you build a map of the environment, and you use this map to stabilize or then to identify obstacles and fly from A to B. This is called vision-based, map-based localization and navigation. But there are many challenges now if you want to not just hover and fly, but flying fast, flying agilely. First of all, drones are one of the few platforms where perception and action are tightly coupled. What does it mean? Well, the problem is the field of view of the camera. So consider this drone. It's a very simple example, but it shows the point. Consider this drone that has a camera pointing down with a limited field of view indicated by the blue cone. The yellow star denotes all the texture that the drone needs to observe at all times in order to hover. Now, say that the drone wants to reach a goal. Because a quadcopter is under-actuated, it cannot stand in any orientation. But as you tilt, you will move. So in order to actually reach the goal, the drone will have to point its thrust vector towards the goal. But by doing so, it will lose the visibility of the features that it needs for doing state estimation. And what will happen? The drone will crash. How do you avoid that? Well, by creating a synergy between perception and action via perception-aware, for example, model predictive control. So that you decide and select trajectories that facilitate the perception task. There is another problem with agile drones. You cannot train your computer vision algorithms for a specific kind of scenario, because drones fly in 3 dimensions. They roll, they pitch. So if you want to train your YOL object detector, you need to do it in principle for a lot of altitudes. There is also additional problems like unmodeled effects, motion blur, high dynamic range, and vortices, turbulent flow. We're going to talk about that. Finally, there is also latency. We are going to talk about that. So the problem with standard cameras is that they sample the scene at constant time intervals. But what happens in between? If you want an agile robot, you need faster sensors and algorithms. You would like to see in the blind time between 2 frames. And then there is another problem. Are drones rigid or soft? Well, under high accelerations like those in drone racing, drones behave as soft robots. Look at this. You see, in order to isolate the vibrations from the motors to the body, we put dampers. But the problem is that dampers change the extrinsic parameters between the camera and mute board and the body frame of the drone. An error of 1 centimeter in miscalibrating these extrinsic parameters can cause an error between 0.5 and 2 meters of state estimation when flying agilely. And these are systematic errors. So we are going to address all this problem, or at least trying, but we need to understand how drones are being navigated. So drones are navigated exactly like any ground other robot. So we have 3 models: perception, planning, and control. Perception does a state estimation, which for a drone means position, velocity, and orientation. And perception also does local 3D mapping via SLAM. Then we have the planning module that selects the ideal trajectory, and then we have the control module that selects the control speeds to follow the given trajectory. This architecture has worked for 40 years of robotics, so there is no reason to actually change it, but it is fragile to imperfect perception and unmodeled effects. How do humans navigate drones? Well, with a single neural network that maps sensory inputs to control commands. So humans are the living proof that one day researchers will achieve in mapping end-to-end sensory motor policies. But the problem is that even if we succeed at doing that, this architecture will have limited interpretability, and they will need billions or trillions of images to train it for any task and any environment. So what we have done over the past 7 years of research in my lab is trying to combine model-based approaches with neural networks. And I will tell you how. The problem when you introduce neural networks is that 3 questions arise. Should we train it with supervision or without supervision? And how do you get enough training data? Can you get them in simulation? So I show you that actually we use massively simulation, but when you use simulation, there is a simulation to reality gap. Now, when we do research, we need to focus on specific tasks. So we picked 3 tasks that allow us to measure our progress with respect to human pilots, but they are not necessarily the most useful ones. It's like Boston Dynamics doing parkour, but they allow us to push the limits of research. So we picked acrobatics, navigation in the wild, which means in unknown environments, and drone racing. But we also had to build an agile drone. So we reached out to the Swiss champion drone racing pilot, Marvin, which I will introduce in a moment. And thanks to him, we built a new platform that was very agile. In fact, it can fly from 0 to 100 kilometers in less than a second, making it faster than a Formula One, which takes 2.6 seconds. We put an NVIDIA Jetson as the brain and Intel cameras as the eyes. The drone is about 20 centimeters in diameter and uses the same motors as FPV pilots, first-person view drone racing pilots. So thanks to machine learning, we were able, for the first time, to fly outside of the lab. Here you see the two examples I mentioned before, acrobatic maneuvers and navigation in the wild. The drone is relying only on its onboard camera and computer. Thanks to machine learning, we were able to double the speed with respect to using standard model-based approaches, and we make the navigation algorithms much more robust to unmodeled effects of perception, like missing data, motion blur, changes of light, and so on. But we needed a lot of data. So what we did is that we relied on massively parallel simulation. We simulate hundreds of drones that do different things. And our simulator has improved over the years. We started with Gazebo, and then we moved to one that we called Flightmare, that is based on Unity or Unreal Engine, and relies on basically video game engines. We could simulate hundreds of drones and learn a navigation policy for acrobatic maneuvers and flying in the wild in just one night, so about 6 to 8 hours, where we simulated the equivalent of about 60 flight days. 24/7 flight, no interruption. Simulation is fast, is cheap, and most importantly, it is safe. Because especially when you fly safety-critical systems like drones, you don't want to endanger your life, that or your researchers, and also damage the environment around you. So it allows you to actually scale up. But the problem is, how do you train these architectures? We train it with imitation learning, where the idea is that you have a neural network that we call the student, that at simulation time tries to imitate the output of an expert. But this is not a human expert. It's actually an artificial expert, the best model-based approach, which unfortunately it's too slow to run very fast in the real world. But it doesn't matter, because what we are doing in simulation is that we distill the model-based expert into a neural network that runs super fast on board. Now, the works I presented, acrobatics and navigation in the wild, relied on imitation learning, which means that you rely on labeled expert data. But not every task allows you to rely on labeled expert data, annotated data. Drone racing is that one task, for example. How difficult is drone racing, and why isn't there an artificial expert that can solve drone racing? So let's try to understand it. I want to introduce you to Marvin, who started racing at the age of 12, and we started a collaboration when he was 15.
Get ready on the toes in less than 5. Beep!
So the racing is a sport where the pilots are always pushing the platform at their physical limits. And every little mistake can lead to a crash. And eventually they always crash, because they want to reach the finish line at non-zero speed, at the maximum speed. It requires quick decision-making and quick reflexes. So it's very difficult, and it takes years to reach this kind of performance. So Marvin is a world-class pilot. And thanks to him, we managed to basically try to do research on drone racing. Now, how would you address the autonomous drone racing problem from an optimal control point of view? In drone racing, you are tasked to pass through a sequence of gates in a given order in minimum time. So what you want to do is to compute the control inputs u of t that minimize flight time through a series of gates. So you want to minimize this integral, subject to different constraints. But there is one constraint that is very, very difficult. It's perception constraints. Why? Because you are relying on onboard state estimation. And when you fly so fast, there is motion blur. So you need to know a priori which trajectories will alleviate motion blur. Not only, you're also looking at the gates, because you're also adjusting, accommodating your trajectory with respect to the gates you're going to pass through. So you need to generate trajectories that are perception aware, that, for example, face the camera towards the next gate, while alleviating motion blur. So it's a chicken and egg problem. And it's very, very difficult to put this into an optimization. But nevertheless, what we did at the very beginning is that we assumed, like at the time of Raf Andrea and Vijay Kumar's works, let's say, let's assume we have perfect localization. What would the problem be? So if you have perfect perception or perfect localization, then you can easily solve the problem by decoupling the problem into planning and control. Since you know the map of the gates, perfect. In fact, pilots have access to the track weeks in advance so that they can practice until the last day. Since you know the map, you can generate the so-called time-optimal trajectory. Look at this animation. So we devised an algorithm that allows you to numerically optimize a certain objective function in order to compute the time-optimal trajectory, considering all the quadrotor constraints and objectives, except perception. We found, therefore, the theoretical lower bound, the ideal time-optimal time, lap time. But there was a bit of a problem. This optimization took more than an hour, and it scales with the number of gates. So another PhD student, Angel, started working on model predictive contouring control, where the idea is that you not only minimize a residual with respect to a reference trajectory, but also you try to maximize your progress towards the next gates. By doing so, we managed to make replanning possible within 2 milliseconds. So we went from 1 hour to 2 milliseconds. If you're interested, I can tell you more. But the problem is that the performance was inferior to that of human pilots because of our model defects. And by the way, in all this research, we were still assuming perfect localization from a motion capture system. Now let's go to the real case scenario. You are actually not using a motion capture system. You are using an onboard camera. It's egocentric perception. You are perceiving the world from your own perspective, your eyes. What's the problem? How do you estimate your motion, your state? Well, you can use an algorithm that was invented in the 1980s, perspective from endpoint, that allows you to triangulate the position and orientation of a drone from 4 visible points. But there is a problem. The uncertainty scales quadratically with the distance from the gates. Here you see the ellipsoid of uncertainty that shrinks as you get closer to the gates and grows as you get far from the gates, quadratically with the distance. And this does not even account systematic errors due to the dampers that deform the platform shape. Because of these reasons, we realized that the optimal control was not going to succeed. We tried, it didn't succeed. But we found a success with a neural network controller that was trained with the reinforcement learning. And it was trained with domain randomization in order to cope with the varying state uncertainty of the platform. But you need a lot of trials and errors, millions of trials and errors, so no way you can train this in the real world. You're going to crash millions of drones. So we actually trained this entirely in simulation. Here you see 100 drones that are learning first to hover, then to fly, and finally to race. The simulation took about an hour, and in this simulator, we were actually simulating the equivalent of 1 month of actual flight, 24/7, without interruption. To get to this point, it took us 7 years. And here I'm explaining that in just 5 minutes. After 7 years of work, in June 2022, we thought we were confident enough to try to challenge the two world champion drone racing pilots. There are two leagues of drone racing, the Drone Racing League and the Multi-GP International League. And we invited the best champion of each league, Alex Vanover, who, by the way, is very famous. He does drone footage for Hollywood movies like Gran Turismo, Ambulance, Red Notice, and many more. Thomas Bitmatta from Australia, our Swiss champion Marvin, and then they had the opportunity to fly against our AI drone, which we friendly named Swift, which means agile. Important is, both the human drones and the AI drones were identical. We built Swift according to the specifications of the two world champion pilots. And they came 1 week in advance, they practiced with the drone and in the truck for many days, 7 days, until they were ready. Now I'm going to show you the summary of the competition, shot from the perspective of the human. The AI Swift is in blue, the best human, Alex Vanover, is in red. Swift won, of course, otherwise I wouldn't be here telling you this story today. What was the margin between the human and the AI? It was at 0.5 seconds. Is this a lot? Yes, it is significant, because in these competitions, typically the difference between the first and the second place winner is 0.1 seconds. Not only was Swift faster, and by the way, I have a lot of backup slides to show you which maneuvers made it become so fast, because it discovered trajectories that humans could not even think of. But also it won the majority of the races, 15 out of 25. The papers were published in Nature and Science Robotics. What we describe in Nature is the entire system, but you have to think that we didn't just do one competition. There were more than 1,200 competitions taking place, both during the practice time and the real competitions. All the trajectories have been released to the public, and also the images, synchronized with IMU and motion capture data, if you want to play with them. All the statistics with 1,200 trajectories can be found in the paper. But there was a problem. I told you that we are relying on massively parallel simulation, but was simulation enough? No. Because now you want to perform the humans in the physical world, is not qualitatively, but in a specific metric, lap time. Simulation doesn't capture all the non-idealities of the real world, systematic errors, turbulent flow. So as you can see, there was a simulation to reality gap. The trajectory in orange was the one simulated in our realistic simulator, which is not perfect, and the one in purple was the trajectory flown by the actual drone. So when we flew the trajectory learned in simulation, the control policy learned in simulation in the real world, our performance was below the human pilot performance. So what did we do? And why was it the case? One reason is aerodynamic effects. Here you see our drone, for example, doing this turn at 70 kilometers per hour in the smoke, and then we took a picture. You can see these vortices. These are caused by motor-to-motor interactions and the fact that the drone flies in its own downwash. This is turbulent flow that if you really want to model it, you need a CFD. Computational fluid dynamics don't take hours or days, and it's always only for a specific trajectory, so you cannot do this at 30 times a second. So we studied in a paper some years ago how to use neural networks to learn the residual forces and torques that cannot be explained by standard physics, like blade element momentum theory. So what we do is the following. We do sim to real to sim to real. And that was one of the key enablers presented in the Nature paper. We first trained the policy in simulation, and we fly it in motion capture the first time to collect additional data that allows us to capture the residual models of perception due to systematic errors, and aerodynamics due to turbulent flow. Then we use this, we fit a neural network model. Then we use this learned model to fine-tune the policy in this improved simulator. And finally, we fly in the real world with onboard perception, no motion capture anymore. What else did we discover? We discovered that actually reinforcement learning is better than optimal control at racing. I'm not saying at anything. In this paper, we did an empirical comparison between reinforcement learning and different optimal control approaches, and we showed that the reason why optimal control was defeated by reinforcement learning is because optimal control decomposes the problem into planning and control. This decomposition limits the range of behaviors that can be expressed by the controller. In contrast, reinforcement learning can directly optimize a task-level objective, which is a very sparse objective, and it can leverage domain randomization to cope with model uncertainty and discover more robust controller performances. We can talk also about it later if you want. But so is therefore the game over? When people see these videos, they think, oh, therefore AI now is better than humans, especially that it was a hype in the media. Well, of course not. As you all know, as roboticists, that's just in a controlled environment. There was a specific hangar. We controlled the illumination. Actually, the firefighters asked us to open the hangar doors in case of an accident or a fire, which there was, by the way, because a drone crashed, destroyed the battery. It exploded. It caused toxic gas, and we had to evacuate the audience for half an hour until we could continue again. So perception is a problem still. So the drone was easily blinded by the external light when we opened the doors. So there is a lot of challenges. I would say that the biggest challenges ahead for robotics are robustness and versatility. Versatility being the capability of the robot to adapt to different tasks and scenarios. Robustness means, of course, that it should work 100%. And let me show you some behind the scenes, some spectacular crashes. So we destroyed the drones hundreds of times over the past few years. We built 60 drones just for the races. But we are not the only ones to fail. The point is that if you want to push the limits, you need to fail thousands of times. If you don't crash, I tell my PhD students, it means you haven't pushed the limits enough. So we need to crash, we need to destroy, we need to fail. So where do we stand in our plot? Well, we are still well behind humans, so I don't know how long it will take. It will take a decade, 2 decades, I don't know. There is still many challenges ahead. But now this is an opportunity to open up the next chapter, which is how can we increase the robustness and the safety, for example, of robotic systems, not necessarily drones in general. For example, talking about human pilots, is there something that is better than human pilots? Yes, birds. This is a sparrowhawk that can slalom among obstacles and flying very agilely. Why are birds faster than human pilots? Because differently from human drone racing pilots, their brain is on the aircraft. Think about it. Human drone racing pilots perceive the scene from the drone perspective through an artificial cameras, frame-based, that transmits frames, actually at 120 Hz, to their eyes. While when you sit on the aircraft, there are no frames. You continuously receive a stream of information. And so this gives us the opportunity to talk about sensing latency versus agility. The agility of a robot is limited by the latency of its sensors and algorithms. I guess everyone agrees with that. If you want to fly faster, you need smaller latency and faster algorithms. Let's look at frame-based cameras. You sample the scene at constant time intervals. For example, 30 Hertz means every 33 milliseconds. Every time you capture a frame, you need to process it, and that takes some time. And then you need to wait for a certain latency, which depends on the frame rate of the camera. So if you want a 1 millisecond latency robot, what do? you increase the frame rate to 1,000 FPS. And each of our smartphones has a 1,000 FPS camera now. But what's the problem? What do you pay? You pay in bandwidth. How do you reduce the bandwidth? you reduce the frame rate. But there is an inverse proportional relation between bandwidth and latency. Bandwidth is proportional to 1 over delta t. So frame-based cameras have this problem that we call the bandwidth-latency trade-off. Whichever camera you choose, you can only move along this blue hyperbola. If you want low latency, you need to sacrifice your bandwidth. If you want low bandwidth, you need to sacrifice latency at the cost of possibly killing people. Event cameras are the only sensor that allows you to get away from this curve. You can choose the bandwidth, you can choose the latency. What are event cameras? Event cameras are sensors that measure only motion in the scene. Here you can see a pictorial illustration of the output of an event camera. I'm moving my arm, and those pixels that detected the motion trigger information. But the output is not frames. It's an asynchronous stream of events in space and time. Imagine that we have a rotating disk as the visual stimulus. The output of the event camera would be a spiral of events in space and time, because only those pixels that detected the stimulus would trigger information. This information comes continuously, not at frame time. That's the key advantage. And you can decide which bandwidth you want to have by tuning the threshold, the sensitivity of the camera. But the problem, though, is that because the sensor is asynchronous, you cannot apply standard computer vision algorithms that were developed for the past 60 years of research. So how are event camera data processed? They are processed according to two different schools of approaches. Here I try to summarize the past 10 years of research of event-based vision. One school of approaches is called event-by-event methods. What they do is that they use the measurement principle of the event camera. What is it? It says that an event is generated whenever the difference of intensity at the same pixel passes a threshold. Thanks to these algorithms, people have managed, for example, to allow inter-frame feature and object tracking, where the idea is that you detect features in the frame and you track them until the next frame, so in the blind time between two frames, event by event, ideally. The second school of approaches is that they use batch methods. So they use a collection of events in space and time. And the idea is to compute, for example, for the case of feature tracking, the motion trajectories of the features according to the direction of motion that generated them. So it's a chicken and egg problem. You need to optimize over the motion parameters that you basically generated that exact space-time volume of events. But these are batch methods, so they increase a little bit the latency of your system. But they're very good for training machine learning algorithms for event cameras. Now, what I'm going to show you in the next few slides is a few examples of how event cameras can unlock scenarios that are inaccessible to standard cameras. If you are familiar with quadcopters, you may know that because of the principle of conservation of the angular momentum, if you break one motor, then the drone will start spinning on itself like a ballerina, right? So what you can do is unstable hovering. And Professor Raffaello D'Andrea from ETH Zurich 10 years ago showed that if you use GPS or motion capture, thanks to position information, you can basically control the drone to remain stable or follow a trajectory. But it was limited to use an external infrastructure. Why? Because when you use onboard cameras, at those rotational speeds, you experience a lot of motion blur. But this is not the case for an event camera, because an event camera does not experience the same motion blur, not at the same level as a standard camera. So here what you see in this video is the drone that is spinning on itself after inducing the failure of one motor. The drone is spinning, and here you see standard frames that are motion blurred, so you cannot track features. event frames and the event raw data, which doesn't experience motion blur. Thanks to the non-motion blur capability of event cameras, we were able to design a state estimation algorithm, which we call the ultimate SLAM, which allows us not only to hover unstably, but even to follow a given trajectory unstably, so to have a controlled trajectory flight. What about latency? Because the events come one after the other one with microsecond resolution, you don't need to wait for the next frame. And also the bandwidth is very limited. So we were able for the first time to have a perception latency of 3.5 milliseconds for dodging balls thrown at the drone. Here, my student Davide is throwing balls at the drone, and the drone is basically trying to evade it. We were able to show that this works quite well with an 80% success rate with a given angle of attack and relative speeds up to 10 meters per second. What about standard cameras? Well, we show in the paper that with standard cameras, you cannot do it at the same relative speeds. You will need to fly significantly faster in order to do such an evasive maneuver. By the way, last year, we showed, in collaboration with Marco Hutter, that the same control algorithms can be inverted, and instead of avoiding the ball, you can catch them in the air with a net on the legged robot. Now, I want to show you also other expansion of applications of event cameras beyond the ones that I talked about so far, like drones and mobile robots. I want to talk about industrial robotics. This is actually work done by the group of Professor Yahya Zwairi at Khalifa University in Abu Dhabi, that in collaboration with Strata and Boeing, they used an event camera to increase the productivity of countersink inspection. Countersinks are these holes where you're going to screw the screws, and they need to be inspected before you start assembling wings, for example, for Boeing planes. Typically, this inspection is done with LiDAR or with cameras, and it's very slow. Why? Because it does stop-and-go motion, like you see in this video. The arm has to stop at every single hole in order to inspect it, in order to avoid motion blur. But with an event camera, you can avoid that. You can do the inspection 10 times faster. What's next? What's the future of event cameras? Well, while the past 8 years of event cameras research were devoted to a single event camera, or only event cameras, now people are looking at the combination of event cameras with standard RGB cameras for two reasons. First of all, because RGB cameras provide intensity information. Second of all, because they have a higher spatial resolution, megapixels. But event cameras are complementary because they sense the information much faster, so they have a much higher temporal resolution, so they are the perfect completion of each other. And we have started a collaboration with a top-tier automotive company to try to transfer some of these results, and the paper is going to appear in a few weeks or months. It's about low-latency automotive vision. By combining an event camera with a standard camera, we can see in the blind time between two frames, and we can detect vehicles or pedestrians before they even become visible by the standard camera. How did we do that? How can you enable now detecting an object or a person event by event, not from dense representations like frames? Remember, an event camera streams information in space and time. So there is the time dimension, which is continuous, it's dense. Now, what we do is that we convert that volume of space-time events into a graph of nearby events. And each node of this graph is updated asynchronously as a single event arrives using an asynchronous graph neural network that we devised for the first time. This asynchronous graph neural network allows updating the nodes asynchronously at the resolution ideal of single events or actually groups of events in order to make it faster. And what we discover is that if you use an event camera in combination with a 20 frames per second camera, you can achieve the same latency as a 5,000 Hertz camera with a bandwidth of a 45 Hz camera without compromising accuracy. What's the future of event cameras? Well, let's start from the history of event cameras. Event cameras were invented by Professor Toby Delbruck at the University of Zurich in 2008. At those times, the pixels were very large, 40 microns, and so you could only accommodate 100 by 100 pixels. Then another competitive company, Prophecy, based in Paris, they put more money, and they managed to miniaturize the pixels to 15 by 15 microns, and they managed to pack a VGA resolution sensor that was 10 years after the invention of the first event camera. In 2019, Meta and Apple started publishing more than 100 patents on event cameras, only in that 1 year. In 2021, Sony, Samsung, and OmniVision, that makes 3 of the largest camera companies on the planet, they started investing in event cameras, and they put out their first event vision sensors, where, thanks to their richness, they managed to miniaturize the pixels to below 5 microns and increase the resolution to over a megapixel. In 2022, Meta opens the first event-based sensing lab, and in the same year, ESA put in space 3 event-based cameras, 2 on the space station and 1 on a CubeSat satellite. Last year, again, Qualcomm and Prophecy, which is the company that scaled up the event camera after the first invention, they partnered together to put event cameras on smartphones. And in academia is actually also improving. So the number of papers on event vision is also increasing. So I think there is a lot of promise ahead and a lot of things that can be potentially done. With this, I would like to thank you, and especially my amazing team, for your attention. Thanks a lot.
Thank you, Davide, for the amazing talk. Are there any questions from the audience?
Thanks for the amazing talk and showing these great results. It's always a pleasure to attend one of your seminars. So my question is more a challenge to a statement you said during your talk for the sake of discussion, let's say. So
I already know where you're going.
Yeah, so you said that birds are better than pilots, better than drones.
Yes.
Because of the perception, latency in the perception and so on.
They sit on the aircraft, because they sit on the aircraft.
Yes, exactly. But the way you phrased it is that you put the emphasis on the perception. It's basically a perception problem, perception gap, let's call it like that. While my challenge, I want to challenge this hypothesis or this conjecture that you have, that in my view, actually there is also a lot of gap from the point of view of control and design of the bird itself, and let's say all the material that is used and many other things that are way beyond perception. So what do you think about this?
Yes, absolutely. So here I was obviously talking in the context of quadcopters, which are mostly rigid, except for this softness I talked about. Now when you start talking about birds, there is a lot of uncertainty there, aerodynamics, but also especially lots of shapes, deformation that you need to model very well. So there are plenty of experts here that are working on this, and also ERC grants. We are collaborating with, in this context, with Dario Floreano, who has also, a Dix Hawk. It's a platform that has wrists on the wings, and that can basically morph its shapes. For example, following a trajectory accurately. And indeed, their aerodynamics is very difficult. Not only do you need to ensure a perception-aware control, but also the aerodynamics is very difficult. And there, for example, we are doing a lot of system identification, classic system identification, but also at the same time, we're also looking again at using neural networks to estimate residual forces that act on the platform that cannot be estimated with standard models. So I think there, again, there are a lot of opportunities.
Thank you for a nice presentation, Davide. It's really impressive what you have actually managed to achieve using quadrocopters. And my question is, how transferable is the conclusion that you actually draw by using quadrocopters to other application areas? And have you also done some experiments, or maybe actually are you planning to use event cameras on other robotic systems in order to gain some insight that might also be beneficial for the drone applications?
Yes, we have plenty of collaborations. So we are collaborating with Volocopter, which has 18 rotors, to basically give them an additional point of failure, so vision-based navigation. Because at the moment they rely on an onboard pilot. Later, they will, once they get the certification, they will go with GPS, and in a decade from today, they hope to have also additional sensors like LiDAR and vision-based. But it has to be certifiable, and that's a problem. So another research opportunity, certifiable perception. Event cameras, safety. I mentioned that we have collaborations with the top-tier companies, and they're about, for example, automotive. I showed also an application there for industrial manufacturing. So in general, all applications where a fast response time is necessary. At the moment, the main application of event cameras is for industrial automation and precision counting. So, for example, detecting objects thrown on the conveyor belt very quickly, recognize them quickly, faster than a time-of-flight camera, and, for example, counting objects that are running through a pipe very quickly with a piece of accuracy.
Thanks, David, for the presentation. So you talked about the advantage of the event cameras, but what will happen if there is no any distinction between the two events? For instance, if you are working in a stationary situation.
If you're working on?
A stationary situation, there is no any specific distinction between two events. So what will happen in those kind of situations?
You use a standard camera. That's why I say that the event cameras and standard cameras are complementary. Not only because of their different temporal resolution and spatial resolution, but also because they don't trigger information when they are stationary. An event camera is a high-pass filter. So it only carries the varying component of the visual signal. There is no information when it's perfectly still, unless you have some tiny jitter. One thing that we explored at some point was taking pictures of the moon with telezoom, with the event camera, when you have the natural shaking of your hands. Have you ever experienced that? It's very difficult. But there are algorithms now that can take advantage of this natural shaking of your hand to basically de-blur the image. And this is something that, for example, Qualcomm and Prophecy are exploring when they now will launch event cameras on the Xiaomi phone, where basically they presented at CVPR last year an application to motion de-blurring for high-speed sport events, for example.
Thanks.
I think we should close the session because there's another session starting in 5 minutes. So thanks a lot, Davide, again. Thank you.